Swayam Prabha. Digital India. Educated India.
Where we shall be broadly discussing about the concepts of processes and threads in an operating systems. Now, these are very important concepts because these processes and threads are something like the basic building block of all the programs and activities that are going on inside the system. And so, there are many things that we shall be discussing later, which will be based on the essential idea about processes and sometimes also threads. So, we start with some discussion about processes, what processes are and why are they important in the context of an operating system. Let us see. Now, I mentioned earlier very briefly that a process, whenever we refer to it by this name, is essentially a program in execution. So, here we shall first try to understand clearly this notion. What do you mean by a program in execution? Now, you see, whenever we run a program on a computer system, for example, suppose we are writing a program in C or C++. So, what do we do? In the first step, we compile the program, then after compilation, we generate the executable code. The executable code is stored in some place on the hard disk, and after we store the executable code in the hard disk, later on at some point in time, we may want to run the program. So, when you run the program, the executable code which was residing in the hard disk, that gets loaded into memory and the process of execution starts. So, basically what I mean to say is that a program which is nothing but an executable file which we are talking about is usually stored in secondary memory. For example, we have a disk. This is my secondary memory. Let us say this is a disk. So, all my executable files will be stored in this disk. Okay. Let us say I have a program stored here, I have another program stored here, another program stored here. These are the so called executable files corresponding to the programs. These are all stored in the disk. Now, when we give a command to run the program, let us see what are the things that happen. So, when we run a program, there are a few things which happen. First thing is that this is the disk image I am showing you. In the computer system, there is also memory. So, by memory I am referring to main memory. So, whenever we want to run a program, the first thing that happens is that this program will be loaded into main memory, because when the processor or the CPU is running a program, it has to fetch the instructions only from the main memory and execute it. So, unless the program is residing in the main memory, it will not be able to execute it. Okay. So, first thing is that the program must be loaded into main memory. Now, in the earlier generation of operating systems, the entire program was loaded into main memory. Whether you required the whole part or not, the entire part was loaded into main memory and then it was executed. But in the modern versions of the operating systems, we shall see later that it is not necessary to load the whole of the program, but only the parts of the program which we are requiring now, we can load those parts into memory before the execution can start. Okay. So, that is why we are saying that loading can be done either fully or partially depending on the kind of system, the kind of memory management support the operating system provides you. And we shall be seeing very shortly that when the program is loaded, not only the program, some other areas of the memory are reserved. Okay. So, these additional memory areas which we are talking about, these are also reserved, and we shall see they have very specific purposes. It can be data area, stack area, and there can be other areas also we shall be mentioning. And after everything is created, the executable code is also there somewhere in the memory. There is a starting address of execution. So, what the operating system will do, it will initialize the program counter with the starting address of the program, so that the next instruction fetch will be continuing starting from that particular address. So, the program starts executing. So, essentially the control is transferred to the first address of the program, and it is done by initializing the program counter. This is normally done by some kind of a jump instruction. So, for jump or branch instruction, essentially the program counter gets loaded with the address of the instruction from where you want to start executing next. Now, another point to note is that we are talking about a process as a program in execution, but in almost all operating systems today, there can be multiple processes which may be running in a system, which may be loaded in a system at a given time. Okay. So, how to manage these processes, in which state these processes are, these are something which also needs to be managed and kept track of. Okay. These are a few things which we shall be discussing. Before that, I said that when a program is loaded into memory, there are various sections of memory that are reserved for specific purposes. Now, let us explain that, but the various operating systems use slightly different terminologies. The terminology that we are using here, this is consistent with the ones which is followed in Unix or Linux. Okay. The various parts of the program, that is when it is loaded in memory, they are called sections. So, a process will consist of a number of sections. Basically, when I talk about a process, I can conceptually say it consists of a number of different sections, section 1, section 2, section 3, and there can be multiple such sections. Okay. Now, there are a few sections which are essential. There are a few sections which may be there, may not be there. Let us first look at the essential sections and what their purpose or role is. Now, following the Unix or Linux terminology, the first section that comes is the text section. Now, again I am saying it is the name that we have borrowed from Unix or Linux. Text section is nothing but the code section. It is the part of main memory where the executable code gets loaded. So, the executable code when you load it into memory, the portion of the memory where that executable code is loaded, that is called the text section. So, basically it is the section where the instructions for the executable program code is stored, right. Then comes data section. As the name implies, some kind of data is stored in this section. Now, we shall be showing an example later exactly what kind of data are stored, but for the time being remember that in a program there can be global variables, there can be local variables. Essentially in the data section, the data values that are stored, they are either global variables or they are statically allocated variables. Global variable means, you see, whenever you have a program consisting of a number of functions, the global variables are those which can be accessed directly by any of the functions. It is not that it is only local to a function, not like that. Similarly, statically allocated data is also something like that. Whenever you call a function, the function call returns, but the value of the statically allocated data does not change. Okay? So, such data are stored in the data section. Then comes a very important section called the stack section, where some kinds of temporary data are stored. Now, you may be knowing whenever you have a function call, there is a process of function call and return. When a function is called, the return address in the calling program has to be saved somewhere, so that after the function execution is complete, it must come back and resume execution from that point. Usually, these return addresses are stored in a stack. You may be knowing stack is a last in first out data structure. The data that you put into the stack in the last will be the first one that you will be taking out. Okay. Now, function calls and returns, they follow a very nice last in first out structure. You can have a nested function call, a function A calls B, B calls C, but when C returns, you return to B, when B returns, you return to A. So, that is last in first out kind. So, inside this stack you store a number of things, most importantly is the return address, as I said. When you are calling a function, there can be some parameters with which you are calling. So, all parameter values, they are also stored in the stack, and all variables you are defining inside a function, these are called local variables. Local variables are visible only from within the function. Whenever the function returns, the local variables are all destroyed. Again, when you call the function, they are again created. They are allocated space inside the stack. Stack is a temporary data, sometimes it is there, sometimes you take it out. Okay? And the last of the essential section is called the heap section, where some kind of dynamically allocated memory space is maintained. Well, in C or C++, for those of you who are familiar, you may be knowing that there is a system called malloc, memory allocation. Using malloc, during execution, you can allocate some space in memory. Now, this space gets created inside the heap section. Okay? This is typically what a process looks like, comprises of these 4 sections. Now, we shall be seeing later that in addition to these 4, there can be some other sections in a process, like for instance, you can define a shared memory segment. A shared memory segment is something which can be shared by 2 or more processes. So, whenever you create a shared memory segment, that becomes a 5th section. There can be more than one shared memory section. So, it can be 6th, 7th, 8th, as many sections as you want. Okay? Fine. So, pictorially speaking, these 4 sections that we are talking about looks like this. These are shown pictorially here. This is the memory map we are showing, and the convention that we are following is that the lowest memory address is on the top, the highest memory address is on the bottom. So, typically the program code, that means the text section, is stored from the lowest memory address, because the size of the code is fixed, you know how much space is required, you keep it there. Similarly, the size of the global variables and statically allocated data section, that is typically kept after text, the size of that is also fixed. Okay. After that comes heap. Now, heap does not have any fixed space or fixed size. As I said, in a heap you maintain information about dynamically allocated memory. So, when a program is executing, some memory space is allocated. When the program returns, or when you free or deallocate that space is again returned back. So, heap can grow, heap can shrink. Similarly, from the other side, typically from the highest memory address, you define the stack. As I said, in a stack you can push some elements and you can pop them out, last in first out. So, stack is also something which can grow, which can shrink, and naturally you start it from the highest memory address. From highest memory address the stack can grow in size, and when you take items out or pop items from the stack, it again shrinks in size. And in heap, when you allocate memory, it is allocated from the lower memory address towards the higher memory address. So, heap grows in one direction, stack grows in another direction. Usually sufficient space is maintained in between. However, if in a program you are requiring too much memory space or due to some error in the program, the amount of memory space you are requiring is growing and growing, then the stack and heap can collide. That will result in some kind of a error, some kind of a segmentation fault or some kind of error you typically get. Okay? This is the pictorial depiction of the different segments or sections in a program when it becomes a process in memory. Okay? And a few things that I have already mentioned are written here, that the stack area is typically initializes with the highest memory address in the allocated segment of the process. When you push data items in the stack will grow from the higher towards lower memory addresses in this direction. Right. Similarly, heap grows in the other direction, heap grows from the lower towards higher memory addresses, and as I said, if memory space is not sufficient or your program due to some error is requiring more and more memory, the stack and heap may collide and you may get some error. Okay? So, there can be a collision between stack and heap. Fine. Now, let us understand the interpretation of these sections with the help of a small program. This program example that I have taken is a C program, which you can run on any machine, but here the example that I have shown has been run on a Linux based machine. You can also try this out. You see, this program is very simple. Here we have declared two variables a and b, int, they are of type integer, and because we have declared them before the main function, they will be global variables. Any variables that you define before the function definitions, that are defined to be global variables. Similarly, I define a pointer called num, then I allocate some space, a space for 10 elements, that means an array of size 10 integers. So, the first address of the allocated block, that is stored in num was a pointer, and then just illustration purpose I am showing that some values we are storing in num. Right. Now, with respect to the sections that I have mentioned, text, data, heap and stack, let us see which of these goes where. Now, the whole program code, this will go into the text section, right. The global variables here you have defined a and b, they will be going into the data section. And as I said, when you define a function, all local variables, they are allocated space in the stack. Now, inside this main function, you have defined two variables, one is a pointer variable num, another is a integer variable c. So, they will be allocated space in the stack. Whenever this function main will be called, they will be allocated space in the stack, and inside the program you are using malloc to allocate some memory space, right. Now, this memory space you are allocating, that will be allocated in the heap region. So, with the help of this small example program, I think I am able to show you that how the different data items and the codes get mapped into the different segments that constitute a process: text, data, heap and stack. Okay. Now, let us look at one thing. Specifically, let us talk about a stack. So, I am not going into the detail of this, I am very briefly mentioning this because understanding of this may be important. Say in a program, a function can call another function. Let us say I have a function A. Function A calls, let us say, a function B. Function B, let us say, it calls another function C. So, you can have a scenario like this, or you can have a scenario where a function is calling itself repeatedly, which you refer to as a recursion or recursive function call. You may be familiar with the recursive definition of factorial, Fibonacci sequence and so on. Now, the point to note is that whenever a function calls another function, it can be a different function, it can be the same function, does not matter. Something gets pushed in the stack. Okay. That something which gets pushed in the stack is referred to as the activation record. Activation record contains a few important information. What does it contain? It contains broadly 3 information. First and most important is the return address. So, whenever a function A calls a function B, somewhere you must store or keep that after the function B is complete, it comes back where inside function A you should, that is referred to as the return address. So, wherever you made the call instruction, just the instruction after the call, that is typically the return address. So, as part of the activation record, you have to store the return address. Then you have to store all local variables. So, in the previous example we said that the local variables num and c, they are allocated space in the stack. See, local variables can be of 2 types: the variables which are defined inside a function or the parameters to a function. For example, you are calling a function factorial, your parameter is a number n. That number n is a parameter that is also like a local variable, that is also kept as part of the activation record. And lastly, the return value. The function can do some calculation, some computation and can return a value to the calling function. That return value is also part of the activation record. So, what happens when a function A calls function B? First, one activation record gets pushed in the stack, let us say activation record 1. Then during execution of function B, it calls another function C. So, what happens? Another activation record gets pushed in the stack, this is activation record 2. Now, when function C finishes its execution, it completes, it has to return back to function B. So, when it returns back, it pops out the last activation record. So, this AR2 gets removed from the stack. So, now the stack contains only AR1. Okay. Now, when function B finishes its execution now and it wants to return back to function A, the last activation record also gets popped out and the stack becomes empty again. So, as you can see, the content of the stack grows and shrinks with time as the function calls are made and function returns are performed. Okay. So, I think I am able to explain this concept at least very roughly to you. This idea is important in understanding a few things. Okay. Now, talking about a process, we have talked about the different sections in a process, the different memory areas in a process: text, data, heap and stack. Now, when a process is executing, the state of the process can change with time. Now, if you look at different textbooks, they have given either the basic states, or in some textbook you will find more elaborate states are mentioned, but we are not trying to make things too complicated. Let us first look at what are the basic states of a process. See, whenever a program is loaded into memory, it becomes a process, and during the period it is in memory, it is executing, the state can change. What are the most important states? Let us see. The first state is called new. New means you are running a new program, you are starting to run a new program. That means a new process is getting created by the operating system. So, in your system there is a new member, a new process has entered, that is, that process is in the new state. Okay. Second thing is that a process may be running on the CPU, on the processor. Whenever a process is running on the CPU, we say that it is in the running state. Now, depending on the system, some of the system can be having a single CPU or a single core, which means only one program can be running at a time, right. So, among a number of processes, only one of them can be in the running state at a given time. However, if your computer system or the CPU has either multiple CPUs or multiple cores, then more than one processes can also be in the running state. Okay. Now, next comes ready. Some processes are running on the CPU, they are in the running state. There may be some other processes which are ready to run. As soon as the CPU becomes available, they can start execution. We say that such processes are in the ready state. As soon as you give it the CPU, it can start running. Okay. Then comes the block state. Let us say a process was running. Okay. During running, suppose it requests for an input or output operation. Now, as you know, we have discussed earlier, the IO operations are typically much slower as compared to the CPU speed. So, whenever there is an input output operation going on, there is no point in keeping the CPU idle. You can let the CPU switch to some other process and let that some other process run. Okay. Now, the process which had requested the input or output operation, that goes into a block state. Block state means right now the process is not running, it is waiting for that IO operation to complete. As soon as the IO operation gets completed, the process again moves back to the ready state, it is again ready to run. A process which is in the block state is not ready to run, because it is waiting for the input output operation to complete, it cannot execute its instructions right now. Once the IO operation is over, then it can again start execution, which means it goes back to the ready state. And finally, when the process has finished its execution, it is in the terminated state. So, when it is in the terminated state, whatever resources the process has occupied, including memory space, that can be released to the operating system, so that some other process can use them. Now, we have talked about so many processes, but how does the transition from one process to another take place? That is something called a process state transition diagram. Let us look into that. This is a simplified version of the process state transition diagram. We are saying simplified because only the basic process states are shown. Okay. The 5 process states that we had shown, new, running, ready, blocked and terminated, these 5 processes are shown. Let us try to understand this diagram a little critically. Let us talk about the new state. A new process is getting created. So, when the new process is getting created, what happens is that the operating system allocates space in the memory for its different sections, text, data, heap and stack, and then loads all the corresponding values into the sections, and then the process becomes ready to run. So, this process is referred to as the admitting process. When a process gets admitted, a new process is allocated space in memory, the code and other data values are loaded in memory, then it becomes a process which is ready to run. It moves to the ready state. Whenever you enter a process, it directly does not go to the running state. First it goes to the ready state, because some other process may already be running, right. Okay. Talking about the other states, let us first talk about the running state. Running state means a process is executing some instructions on the CPU, that is, it is running. So, if you consider a process, let us say Pi, it is executing some instructions, okay? These are all instructions. So, it is trying to execute these instructions one by one in sequence. Now, what might happen? What are the different things that can happen? First is that the last statement of the process might get executed, which means the process completes. So, the event that occurs is complete, the process has completed, and the process moves from the running state to the terminated state. So, when the last instruction of a process gets executed, which means the process has finished its execution, that is the event which we show in this diagram as complete event, and the state of the process changes from running to terminated. Okay. The second thing that can happen is, as the example that I took just some time back, that the process requests for an input or output operation. Let us say it wants to read from an input device, or it wants to write something into a disk, it wants to read something from a disk, something like that. It is accessing a file. So, whenever such a thing happens, as I said, that process will take a longer time. So, there is no point in keeping that process occupying the CPU during this time, because some other process which was waiting could have used the CPU during this time. So, whenever such an event occurs, input output kind of event, there can be other events which I will talk later. So, we are saying that is a wait for event. Wait for event means some event for which the process will be waiting for, and whenever there is a wait for event, the process cannot run anymore, because the IO operation has been initiated. Unless the IO operation is completed, the process cannot resume, cannot continue. So, in the meantime, the process goes to the block state. Block state means the process is waiting for something, it is waiting for an input or output operation. Okay. Next, let us come to ready state. Ready state, as I said, many processes can be in the ready state. They are the processes which are ready to run. As soon as the CPU becomes available, CPU becomes free, you can run the process on the CPU and execution will continue. So, from the ready, whenever the CPU becomes free, When does the CPU becomes free? Either from a running there is a complete event, or from running there is a wait for event. There is another event which I have not talked about it, interrupt event is also there. So, if one of these three events occur, a process which was in the running state moves to some other state, which means now the CPU becomes available. So, when the CPU becomes available, now one of the ready processes can move to the running state. You can have this particular transition, ready to running. So, whenever the CPU becomes available, one of the ready processes can move to the running state, and this process is called dispatch. This is the event, and this is something which I have not talked about yet. This I shall be discussing again later. See, any kind of interrupt comes, it can be an interrupt from a IO device, it can be an interrupt from a timer. Whenever an interrupt comes, whichever program that was executing, that has to be temporarily suspended and control has to be transferred to the operating system. Operating system will find out what is that interrupt, why it has come, it will try to service the interrupt, and then it will again come back to one of the programs for execution. So, while that interrupt is being processed, the currently running program will temporarily move to the ready state. So, this transition is that. Okay. So, this is the simplified state transition diagram that I have talked about. Now, in this diagram there are a couple of things. Dispatcher, let us try to see what this dispatcher is actually. See, dispatch, what I said, it is basically the transition from ready to running. So, whenever the CPU becomes available, dispatcher, which is a module of the operating system, it is a functionality of the operating system that starts running whenever the CPU becomes free. What is the purpose of the dispatcher? It will see what are the processes that are in the ready state. It will select one of the processes in the ready state and assign it to the CPU. That means, it changes it to running state. Now, we shall be discussing this later again, that how does the dispatcher select the next process from the ready list. There can be a number of policies that the operating system follows. We shall see these things later. Maybe a process with a higher priority will be chosen first. Okay? And actually there can be other policies as well. This dispatcher function or dispatcher module is called or invoked, as I said, whenever the CPU becomes free. That means, there is no process in the running state. The CPU becomes free can be for a number of things. As I said, a process can go for an input output operation, which means it has invoked some kind of a system call. There can be some kind of an interrupt, a timer interrupt, or a process might complete, it has terminated. So, under such conditions, the dispatcher will be called and the next process from the ready list, it will be selected and it will be assigned to the CPU. And the other thing that I wanted to just talk about is, when I say that a process is waiting for an event, that means I am talking about the transition running to blocked. A process was running, some event occurred, it can be a system call, it can be interrupt, something, due to which the process has to wait. So, the nature of the event for which the process is waiting can be various. Some of these we shall be discussing later, you really cannot possibly understand if I tell it right now. Some example, one thing that you can understand is input output operation, that whenever there is a IO operation, the process has to wait. There are some other kind of things a process can wait from a semaphore. It can be trying to do some communication with another process, for example, reading from a pipe, reading from a message queue and so on. These are some instances where again a process has to wait. It is trying to read from somewhere, but data is not available there. Unless data comes, the process cannot continue. It will have to be in the block state. It will have to wait. Okay. So, these are some of the reasons why a process may need to wait for some event, and whenever that event occurs, as I said, the process will move back from the block to the ready state. Okay. Fine. Now, some of the important state transitions, I have already discussed this, I am again repeating because some of these are very important. The most important transition is ready to running. So, I said this is the task of the dispatcher. When the CPU has become free and there are one or more processes in the ready state, dispatcher comes, picks up one of the processes from the ready state, assigns it to the CPU. So, the state of the process changes from ready to running. Okay. Now, in some cases this we have not talked about exactly, the process can change from running to ready. That means, the process was running, for some reason we have taken the CPU forcibly away from the process. It is not that the process is waiting for something, no, process was not waiting, but due to some reason we take the CPU away from the process. We move it to the ready state and give some other process in the ready state to the CPU. See, this typically happens in a time sharing operating system, which we had talked about, where a number of processes are running in the system and the operating system gives typically equal time slices to all the processes. So, once a process has finished its slice, let us say of 2 milliseconds, operating system will forcibly take CPU away from the process and give it to the next process, and that 2 millisecond is counted by a hardware timer. Whenever that 2 millisecond elapses, the timer sends an interrupt, and whenever a timer interrupt comes, the operating system wakes up, it calls the dispatcher, selects the next process in the ready state and swaps the running and ready processes. The running process goes to ready, the ready process comes to running. Okay. Now, the third important transition is running to blocked. So, I said typically it is due to an input output operation or some other event, like I talked about semaphores, I talked about reading from some pipe or message queue, some event like that which prevents the process from continuing its execution. Okay. And last is blocked to ready, a process which was blocked due to some event. Whenever that event has occurred, for example, input output operation, that operation is complete. So, now the process is ready to execute again. So, you move it back to the ready state. Okay. These are some of the important transitions. Now, I said that we talked about the basic transitions, the 5 transitions, but if you look into the states in a little more detail, many more states can come out. In some textbooks you will find that there are many other states which are shown. Now, we are just talking about 2 additional states here which are important, but other states we are not discussing here. So, we are including something called swapped out states in the original state transition diagram. We have included 2 additional states, swapped out ready and swapped out blocked. See, before trying to explain what these states are, let me try to explain how this process and memory management occurs. See, I am again showing you a picture. Suppose this is a disk and this is main memory. This is your main memory. Now, specifically in the disk, there is an area which is called the swap area. See, in some of the modern operating systems, there is no separate swap area. It can happen directly from any other part of the disk also, but generally let us talk about the swap area. Swap area is a part of the disk where copies of the processes that are running are kept. Like in the swap area, I shall be maintain copies of a process P1, P2, P3 and so on. So, whatever processes are running, copies of those processes will be kept in the swap area. And whenever the processes are running, as I said, they will be loaded into main memory. Let us say process P1, process P2, process P3, process P4, they are loaded into main memory. Suppose a fifth process also wants to run. So, they will be just allocated space in the swap area. This is P5, let us say, but what happens is that memory is full, you cannot load P5. So, what you may have to do, some of the processes that again the OS can use some policy which process will be selected. Let us say P2, P2 will be stored back into swap and this new process P5 will be loaded. So, P2 gets replaced by P5. This is called swap out and swap in operation. Swap out means you take a process from the main memory, take it out, store it back into swap area, that is swap out. And swap in means you pick a process from the swap area, load it into main memory, that is swap in. Okay. So, if memory becomes full and there are many other processes which are coming, you may have to swap out some of the processes, that is the idea. Now, say what you can do, there can be many processes in the ready state. Depending on the memory availability, some of these processes you can swap out, it can go to so called swapped out ready state. That means, those are ready, but temporarily you have kept it in the swap space in the disk. Similarly, later on when space becomes available in main memory, you can swap in those back to the ready state. Similarly, some of the processes which are blocked, you can temporarily move them out, swap out, and they will be in the swapped out block state in the disk, in the swap space. And when the event for which it was blocked occurs and it was in the swapped out block state, it can move to the swapped out ready state. It is still in the disk, but you just change the state of the process from swapped out block to swapped out ready. So, just these are some of the extensions that we have talked about, some of the additional states which can take care of the scenario that memory space is limited, more processes are coming, you have to manage memory space. Some of the processes may have to be moved back into disk, some of the processes have to be loaded from the disk. These are swap out and swap in operations. Okay? Fine. So, this is what I am just pictorially showing it once more in a clear way. This is your disk. There is a portion of the disk which you call the swap area or swap space. So, in this swap area you have copies of all the processes that are running. So, when I say copies of processes, it means all the sections, not only the code, text, data, heap and stack, everything. So, all the processes that are running, their images are stored in the swap area, and as I said, you have your main memory where some of these might be loaded, not all, not necessarily all. P1 will be loaded, let us say P2 is loaded, let us say P4 is loaded, but others whenever required you will be loading, and when you do not require you can again swap them out. This is what the operating system manages and controls. Okay? Fine. Now, let us specifically talk about two different types of operating system, and let us see what is the impact with respect to the state transition diagram. First, let us talk about a time sharing operating system. In a time sharing operating system, we have already said there are a number of processes in the ready state. The CPU is assigned to all the processes in a cyclical fashion. The operating system assigns equal time to all the processes. So, to implement a time sharing system, what is done is something like this. You have your CPU which will be running the programs, and you have another hardware which is the hardware timer. The timer can send an interrupt to the CPU. As I said, whenever operating system is giving the CPU to a new process in the time sharing environment, it loads or initializes the timer, and the timer value gets decremented with every clock. Whenever the timer reaches 0, it interrupts the CPU. So, whenever the interrupt comes, as I have said earlier, there is a process of interrupt handling. You go to an interrupt handler which is part of the operating system. That operating system understands that a timer interrupt has come. So, I have to suspend the current process, move it from the running to ready state, take another process on the ready state, move it to the running state. So, you see in a time sharing operating system, these two state transitions occur frequently. See, even if the process is not wanting, but the operating system is maintaining the timer, so that with at the end of every time slice this transition takes place. One process goes from running to ready, another process is picked up from ready, it comes back to running, right. So, in a time sharing operating system, these two transitions become most important, and of course, whenever some process gets blocked due to some event, some IO event, it is not in the ready state anyway. So, that process is not participating in that time slice competition, it is out of that. So, all the processes which are in the ready state, they are in this cyclic competition for the CPU. Okay. Now, let us talk about a multi-programming operating system. So, multi-programming operating system we mentioned earlier, there also the idea is similar, but there is a difference. A process P1 was using the CPU, it was using the CPU, but suddenly there is an IO operation, it waits for IO. So, what happens, some other process P2 which was there already loaded in memory, whenever process P1 is waiting for IO, it can use the CPU to run its code. But the idea is that whenever this IO completion is done, IO is done, so this P2 will be interrupted, and again control will be transferred to P1, P1 will again start using the CPU, and P2 will move to the ready state. This is what multi-programming is. So, with respect to the state transition diagram, let us see what happens. A process was in the running state, it gets blocked due to IO, only then the question of switching from one process to another comes in, otherwise that process itself will continue. So, this event is important here, running to blocked, this event is important, and whenever there is a running to block event, you move a process from ready to running, the next process. But the thing is that whenever the IO interrupt comes saying that well IO operation is complete, there is a kind of IO interrupt. This IO interrupt does two things. One, it will wake up this process. It was waiting for an event, it will go back to the ready state. And secondly, it will also interrupt the current program. The operating system will come and find out that the IO operation is complete. So, it will again resume P1, it will move P1 to the running state. So, in a multi-programming system, we are not giving equal time slice, we are continuing with one process. Only when it gets blocked for IO, we move to another process, and when that IO is completed, we again switch back to that process and continue. Okay. So, in a multi-programming system, so all these different transitions can take place basically. So, we basically talked about the concept of processes in an operating system, the states of a process and how the state transitions can occur. So, to summarize, the operating system tries to maintain information about the processes that are residing in the system, all information, in what state the processes are and any other relevant information that is required. We shall be seeing in the next lecture that when the operating system is trying to maintain information about the processes, there is a data structure which is used called the process control block, in short PCB. There is a PCB which is created for every process. Okay? For every process there is a PCB and operating system maintains the data structure of the PCBs. And one more thing we saw in this lecture today is that a process can be in one of several states, and during execution whenever some event occurs, various kinds of events, the state of a process can change from one to the other. The point to note is that all operating systems that we see today, they have support from processes. They also support another kind of you can say entities similar to a process, which are called threads. This also we shall be discussing. The threads are sometimes called lightweight processes, because we shall be seeing in the next lecture that whenever we make some transition, state transition, for example, ready to running, running to ready, something like that, one of the processes need to be stopped, another process need to be resumed. So, lot of things need to be saved, lot of things need to be restored. This process is called context switch. This context switch overhead is not negligible, this is quite significant. Now, in threads we shall be seeing this context switch can be done very fast, but there are obvious restrictions. So, all these things we shall be seeing in the next couple of lectures in this module. Thank you.